So first, I would like to acknowledge my former PhD student, Musin and Dion, present student Dion, who are involved in this work. And for financial support, I would like to acknowledge ANRF through this SORBSURE and CRG research grant. So I would be talking about inertial chiral active Brownian particle in a harmonic confinement, resonance-like response. So I think we have, by now we have heard many talks based on this active matter or active Brownian dynamics. So let me briefly introduce active matter, which is a special kind of non-equilibrium system, and that is inherently driven away from equilibrium. And the dynamics in it is followed by self-propelled particles, which generate a spontaneous flow by consuming energy from the environment. And these are the typical examples of active matter in both single particle level as well as collective level. So among the active particles, the chiral particles, especially the Janus rod or Janus particles, they are in particular very interesting in the sense because they exhibit an inherent rotational bias in their self-propulsion. So the chirality introduces a persistent angular component that can arise because of the shape asymmetry or structural asymmetry, or maybe due to the asymmetry of chemical composition and so on. So what happens because of this, these chiral particles, they can both self-propel as well as self-rotate. And there, in the recent years in experiments, it is realized that these chiral particles are Janus rods, Janus particles. So they are very much responsive to the boundary or confinements. And in fact, they show very interesting features near the boundaries. So motivated by this, we investigated the dynamics of an inertial chiral active Brownian particle, which is confined by a two-dimensional harmonic confinement. So the dynamics can be described with the same active Brownian framework with, let's say, Vs is the self-propulsion velocity of the particle. And n is the unit vector, which is basically represents the orientation of the particle with orientation angle phi, and that evolves with time like this, with I as the moment of inertia. And the chirality can be introduced to this dynamics by a torque-like effect. That's why here the capital omega is the strength of the chirality. So with such dynamics, we first investigated the particle trajectory. And what we observed that for a achiral particle, that means in the absence of chirality, the particle trajectories are completely random. And that gets directed with increase in self-propulsion velocity. That is what we expect. But for a chiral particle, that is in the presence of finite chirality, when activity is not there, again the trajectory is random. But there is an emergence of a circular motion that we found with increase in the self-propulsion velocity. That means the influence of chirality is much stronger in the presence of higher activity. So further, in order to investigate the transport properties or to characterize the distribution and so on, so we took interest in computing the moments, so like mean square displacement, kurtosis, and so on. So while investigating the mean square displacement, what we observed that for an achiral particle, the steady state mean square displacement shows a monotonic decay with the harmonic frequency. So that is reflecting the role of the confinement, and that is what expected. But for in the presence of chirality or for a chiral particle, this mean square displacement initially decreases with harmonic frequency, and then again it increases and shows a maximum only when the harmonic frequency matches with the chiral frequency. So we further took interest in evaluating the kurtosis of position. As you know, the kurtosis can give a quantitative estimate of how the position distribution deviates from its Gaussian behavior. And this at steady state, it can be defined like this. And the kurtosis takes a typical value of 2 corresponding to a Gaussian distribution in 2 dimensions. And while investigating this kurtosis as a function of the harmonic frequency, what we observed that for lower value of harmonic frequency, the kurtosis exactly takes the value of 2, which corresponds to a Gaussian distribution, and then increases and then decreases to a dip. And then subsequently it increases before eventually saturates at value of 2. So this dip occurs only when the chiral frequency and the harmonic frequency are of the same order in magnitude. So the same behavior is evident when the kurtosis is plotted as a function of harmonic frequency as well as the chiral frequency simultaneously. And what we observe that for higher value of chiral frequency, the kurtosis deviates from the Gaussian value along the diagonal line, and this deviation is not strictly diagonal for lower values of chiral frequency. In fact, in the chirality tends to zero limit, that is for a achiral particle, the particle exhibits a reentrant kind of transition, that is from passive to active and then to active behavior with the harmonic frequency, and that is what already reported by Professor Dhar and Professor Kundu and the team, I think sometimes back. So next we took interest in investigating the marginal probability distribution and orientation profile. So while investigating the marginal probability distribution, what we observed that when the harmonic frequency and chiral frequency are of the same order in magnitude, the position distribution, it transforms from a Gaussian to a platycooty kind of distribution, which characterizes with short tails. And you can see that is a flat kind of flat region around the center of the potential. Which indicates there is a presence of a persistent rotation around the minimum of the potential, and that is also reflected from the particle trajectories. Further, while investigating the orientation profile by computing this one, so and what we observed that when the chiral frequency dominates over the harmonic frequency, the orientation profile that spirals towards the center. So this indicates that the orientation of the particle and most of the position are in opposite direction to the radial, direction. Similarly, when the chiral frequency is dominated by the harmonic frequency, the orientation profile spirals away from the center. So this indicates that the particle orientation aligns with the radial direction. But interestingly, when the chiral frequency and the harmonic frequency are of the same order in magnitude, so it shows the orientation profile shows a persistent rotation around the center of the potential. So that is corresponding to the ring-like particle distribution. So this is like the features what we observe that happens only when the chiral frequency matches with the harmonic frequency. So this is kind of like synchronization happen or resonance-like effect. So then next, so this is very interesting. So we thought of just taking computing this, looking at the same dynamics in the rotationally overdamped limit. That means that is applicable to the systems where the mass of the particle, it is concentrated near the center of mass so that the moment of inertia can be ignored. So in this limit, that dynamics can be analytically tractable. And in fact, we have exactly computed the, just 1 second. So we have exactly calculated these moments like mean square displacement, kurtosis, and so on. So what we observe, we also see that the similar features here. Whereas that means that peak in the mean square displacement as well as the dip in the kurtosis that happens only when the harmonic frequency matches with the chiral frequency. But the peak and the dip were less pronounced as compared to the case in the presence of that rotational inertia. So these are the things that what we just like we can see that the chiral particles are very much responsive to the confinement or boundary, and that is what that's why whenever means that's a kind of synchronization happens. So that is why we see this interesting behavior. So with this, I will conclude my talk. So thank you for your kind attention.
We have time for a quick question.
What transient state? Okay. Yeah, that is what we see. No, that this intermediate time you can see the oscillation. So that may be due to the interplay between the inertia and confinement. That is because that you see for achiral particle also, and that becomes more stronger when in the presence of chirality. So chirality also is a reason for the fluctuation in the intermediate times.
I think for achiral particles, there's been work where they show that the particle escapes from the trap. Do you see anything like that?
Once again.
At very high stiffnesses, or what you're calling the harmonic frequency, people have seen cage escape. So, I mean, the trap escape. Do you see that?
that I think this is a particle gets trapped, I see. A particle gets trapped. That you mean that the stiffness is very high. So then
Okay.
because this is what we see here. This is what the synchronization happens only at the intermediate range of activity. I mean that if the velocity is very high, then also we do not see, or velocity is very low, also we do not see. So there is an intermediate regime that's what this phenomenon is observed. And that's why we took interest in evaluating in the rotational overdamped limit, because analytically that can be tractable. And that we see that the peak occurs at the time scale. So that also depends on this self-propulsion velocity, inertial time scale, and so on.
Thanks.
Analytic computation, you said it can be done only in the overdamped limit or also in the analytic computation you can do only in the overdamped limit of the moments. So you said you can analytically compute the moments, right?
Yes.
Is that only in the overdamped limit or?
Only in the overdamped limit. Now, underdamped limit, that is only simulation.
Because it's still, the equations should still be kind of linear, right?
Yeah, maybe, but we didn't. But you mean that the inertial limit also it is still? Yes, but I think that yeah, we didn't.
Maybe in the session. Yeah. Let's thank Sahoo again.